Hi everyone. In this chapter, a new chapter on graphing techniques, we will be going through the introduction to the graphing techniques in this video clip. So in this video clip, let me just first highlight to you about graphs in general. Now the graphs is actually a relationship between two variables. So that means it's actually a way to draw or to visualize the relationship between two variables, say x and y. However, not all graphs are represented in this kind of diagram. It may actually be represented as a function. So if I define a function in this manner, it basically says that the relationship between x and y is such that if you substitute an x value inside the function, you get a y value. Let's take, for example, a simple example. Suppose fx is x squared plus 5. So this actually relates the x value to this so-called y value. So for example, it maps the value 1 to the value 1 squared plus 5. So that gives you 6. So another situation, like maps minus 2 to be minus 2 squared plus 5, and that gives you 4 plus 5, and that gives you 9. So if we are to represent this relationship in a form of a diagram, then what we are looking at is the graph. So we need to study some of the characteristics of graphs. So the first characteristic is this thing called axial intercept. And what are axial intercepts? There are generally two axial intercepts, one of which is the X intercepts. They are actually the points where y equals 0. That means are those points where the curve or the graph touches or cuts the x-axis. So to be able to find the x-intercepts, we simply let y to be equal to 0. Y to be equal to 0. And from there, you find the x values. The other intercepts is what we call the y-intercepts. Now, the y-intercepts are actually points where x equals to 0. So basically, it will be the points where the graph cuts or touches the y-axis. Now let me give an example. Suppose the y is given by x plus 1 over x plus 3. Now if I let y to be equal to 0 to find the x-intercepts, that means x plus 1 over x plus 3 will be equal to 0. If you multiply throughout by x plus 3, you'll get x plus 1 equals 0, and hence x equal minus 1. So we say that the x-intercepts in this case will be minus 1 and 0. And to find the y-intercept is to let x equal 0. So your y would be 0 plus 1 over 0 plus 3. That gives you 1/3. So that means the y-intercept will be 0 and 1/3. So that is axial intercept. Now axial intercepts have to be indicated on the graph whenever possible. Now the second type of feature that you need to know is the thing called turning points. Now what are turning points? You look at the notes that is provided. It says that turning points are points on a graph where the curve turns, basically. So a turning point can be a maximum or a minimum point. So a maximum point, okay, where the curve turns. Or minimum point, again, another turn. Okay, and these points are sometimes what we call the local maximum or local minimum, accordingly, whether it's a maximum or minimum point. Okay, so, and how do we actually go about finding the turning points? We can actually have to do what we call differentiation, which we will talk about it in our chapter on differentiation later on. Now let's talk about symmetry now. Now for symmetry, okay, there are a few types of symmetry here. We are looking at 4 types of symmetry. The first type of symmetry is what we call symmetry about the y-axis. Symmetry about the y-axis. And what is the definition of symmetry about y-axis? It says that minus x and y lies on the graph whenever x, y lies on the graph. In short, these 2 points lie on the graph. Okay, so visually, if you see as the x and y coordinate system, if I have this point x and y, this point on the graph, then another corresponding point on the graph will be minus x and y. So one example of such a graph which has this type of symmetry is y equals x squared. Because y equals x squared is like this. Okay. So if you let x replace by minus x in this equation, you will still get y equals to minus x squared is still x squared. Okay, so in this example, okay, the points xy and minus xy are on the same diagram, on the same graph. So in short, if you know this part of the graph, you can obtain the other part of the graph by what we call a reflection about the y-axis. Okay, so the second type of symmetry is symmetry about the x-axis. Okay, symmetry about x-axis. It says that if the points x and minus y and xy, okay, if they lie on the graph, then we say that the graph has a symmetry about the x-axis. Okay, one such example is y squared equals x, where the graph looks like this: x-axis, y-axis, the curve looks something like that. Okay. Now this is an example of the case where it's symmetry about the x-axis, because a point here, which is xy, and a point here, which is x minus y, lie on the same graph. So once you know this part of the graph, you can obtain the other part of the graph by a reflection about the x-axis. So that is the symmetry about the x-axis. Okay, 2 more symmetries that I would like to introduce in this video clips as well. One of which is the symmetry about the origin. Okay, symmetry about the origin. And what it says about symmetry about the origin is that if the points minus x minus y and xy, okay, if both of them lies on the graph, then we are saying that the graph has symmetry about the origin. An example of such a graph is y equals x cubed. Okay, if you replace the x by minus x, okay, you will get the following: minus x cubed, which is actually the original y with a negative sign in front of it. So the points minus x minus y as well as xy lie on the graph. Example of a diagram for y x cubed looks like this. So a point here, which is xy, and a point here, which is minus x minus y, both lie on the same diagram. Okay? So if you know this part of the graph, you do a reflection about the origin, you will get this part of the graph. If you know this part of the graph, by reflection of the origin, you get this part of the graph. So there is symmetry about the origin. The fourth and last type of symmetry is what we call symmetry about y equals x. Okay? Now this is where if you x and y yx lies on the graph. Okay? Now when that happens, what we call is the symmetry about the y equals x. One such example is a circle, which you have learned back in your secondary school. This circle, of course, has origin being the center, radius being 2. Okay? So a point here, say x, y, and if you interchange it, become yx. Okay? They lie on the same graph. So it's actually obtained by reflection about the graph of y equal to x. Okay? That means if you interchange the x and y values, x replaced by y and y replaced by x, it will be the same as the original equation. Okay? This is an example of a case when we have symmetry about the y equals to x. Okay? Now we look into asymptotes. In one of the video clips on the previous chapter, we talk about asymptotes, and I promise that I'll be going through that in this chapter. Now, asymptotes. Now, there will be two types of asymptotes that you'll be learning under this H1 course, one of which is this thing called the vertical asymptote. Okay? And the second type of asymptote, we call it the horizontal asymptote. Okay? Now, what is a vertical asymptote? Now, a vertical asymptote, from the definition, it says the line x equals to k, where the curve approaches as y tends to infinity or y tends to minus infinity. So example is y equals 1 over x. Okay? If you let y goes to infinity, okay, or y goes to minus infinity, what happens? Okay? That means x must be really, really very small. Okay? In order for 1 over x to goes to infinity or 1 over x to goes to minus infinity. So in this case, the vertical asymptote will be x equals 0. Okay? Because the value of x where the curve approaches when y goes to infinity or minus infinity. But not every graph has a vertical asymptote. Okay? Other examples of situation where it has a vertical asymptote will be y equals, say, 1 over x plus 2. Okay? This time round, the vertical asymptote will be x equals minus 2. Because when x approaches minus 2, that means this whole thing approaches 0 when y approaches infinity or minus infinity. So in general, for this kind of algebraic fractions, which has a ratio of two functions, the way to obtain vertical asymptote is by letting the denominator goes to 0. Okay? That will be the x values. Okay? Now, comes to another vertical asymptote that is quite famous, is the y equals tangent x graph. In a y equals tangent x graph, the vertical asymptotes are x equals to pi over 2 plus minus 3 pi over 2 and so on and so forth. Okay? If you look at a graph of tangent x graph, it looks something like that. Okay. So yeah, something like this. Okay, so the vertical asymptotes are all these vertical lines here. Okay, now the next type of asymptotes to be going through is this thing called horizontal asymptote. Okay, for horizontal asymptote, the definition is that it's the line y equals k where the curve approaches as x tends to infinity or x tends to minus infinity. So one such example would be like y equals x minus 1 over x. If you use long division to divide x minus 1 over x with x, okay, you 1 times x give me x, then bring the minus 1 down. So this expression can be written as 1 minus 1 over x. Okay, so if you let x goes to infinity or x goes to minus infinity, what do you notice? The y values will go to 1 because this becomes very, very large. 1 over very, very large number will go to 0. Okay, so y equals to 1 will therefore be what we call the horizontal asymptote. Will be the horizontal asymptote. Okay, another example is y equals to x plus 3 over x plus 2. Likewise, if you use long division, you will get the following. So again, if you let x goes to infinity or x goes to minus infinity, your y will go to 1. Okay, so that means y equals to 1 will be what we call the horizontal asymptote. So if the vertical asymptotes are vertical lines, the horizontal asymptotes are horizontal lines. So that means that, for example, in this case, the graph will actually approach the y equals to 1 when x goes to infinity or x goes to minus infinity, very, very large values here. And likewise, you have the vertical asymptote, which is x equals minus 2. Okay, so with this information that you have, you already can get the vertical asymptote, which is x equals minus 2, and the horizontal asymptote, y equals 1. Okay. Finally, the last useful feature of graphs is that of the restriction on some possible values of x and y. Now, in some cases or in some graphs, it's pretty useful to know some kind of restriction of the graph. That means that we will know exactly which part of the graph exists and which part of the graph does not exist. For example, in the graph of y equals sine x, okay, we all know that sine function is such that sine x is always between minus 1 and 1. So this is in a way a restriction. So if you are to sketch a graph of sine x, there will be no graphs above y equals to 1, and there will also be no graphs below y equals minus 1. So in a way, it's a restriction. Another example is y equals positive square of x plus 2. We all know that this expression inside the square root has to be non-negative. So that means x plus 2 must be greater than 0 or x is greater than minus 2. So there will not be any graph to the left of x equals minus 2. Okay? After going through all these features, And then in the next video clip, we'll be looking at some of these questions. Okay, thank you.